Hi there everyone, my name is Nguyen Ky. I'm from TUNA Group. Today we are not here to simply walk through a canned tuna recipe. We are here to tackle a real industrial engineering problem. Because canned tuna is a dense solid pack, it conducts heat poorly. So this presentation explores how engineers manage the heat transfer challenge during the canning process to achieve two goals. Safely eliminating microorganisms and optimizing energy consumption. So looking at the overall system, we can divide it into three strategic parts. Part 1, raw material preparation. This is where we manipulate the initial thermal state, bringing frozen tuna from a safe pre-cooked condition. Part 2, canning and sterilization. This is the heart of the plant, where the most intense heat transfer occurs. Part 3, post-processing and quality assurance. This area handles post-sterilization physical effects, including high-speed coding, vacuum integrity checks, and storage. So for more details, we're gonna go to the canned tuna processing flowchart. So this is three part. Part 1, preparing materials. This is the detail of this part, including receiving ingredients and sorting, freezing storage, thawing, buttering, pre-cook, and cooling. Next, we're gonna to the part 2, canning and sterilization. In this step, we have pouring soup, simming, sterilization, washing, and drying. And to the last part, downstream processing and quality assurance. In this step, we have cooling, inspection, and QC, final packaging, and warehouse storage and distribution. Okay, so here are some fun facts about the F0 value. So the formula is F0 equals delta T times the sum of 10 raised to the power of T minus 121 divided by Z. So the definition, it is defined as a thermal lethality time required to eliminate all microorganisms present in foods by exposing them to a temperature of 121 Celsius degree, and it is expressed in minutes. It guarantees that the lethal pathogens like the bacteria that cause botulism are destroyed to ensure the safety concern.
In industrial processes, the biggest threat is inconsistencies. If you feed the line with the tuna that has a fluctuating temperature gradients where the surface is warming but the core is rock solid, every heat transfer calculations downstreams will be collapsed. To eliminate this chaos, we enforce a strictly thermodynamic anchor. The core of every fish must be locked in exactly -18 Celsius. Biologically, this temperature frees the free water, crushing the water activity level to paralyze manganese, the bacteria that trigger histamine and stop enzymes from turning the meat to mush. This guarantees precise the heat driving force densities for the thawing beans, ensuring we can safely thaw the entire batch well under the strict 12-hour limit. Next, we move to the stationary to the thawing beans. Station 2 is thawing beans natural air thawing a biological time bomb for the histamine forming bacteria. We use 1 ton water beans, but shocking isn't enough. A still water can create a cold thermal powdery layer that acts as an insulating blanket, stopping the heat transfer. To soften this layer, we force up to the 132 liters of water per minute through the corner where the 3D circulations and blast with the air compressors. This violent fluid agitation maximizes the heat transfer. If we just blast the fish with the 100 heat the whole time, the outside burn, the shrink and crack, it squeeze all the water proteins, meaning we lose a lot of valuable meat. But the heat is too low inside, stay raw and dangerous material survives. Solutions, we don't boil the fish in the water. We put the 5 tons of fish into the massive steam chamber. Hot steam touch the cold fish, turn it into the liquid, and release the huge amount of the heat that slowly move into the center. To stop the meat cracking, we lower the temperature step by step. We start at the 100, quickly kill surface bacteria, then drop steam to the 88 Celsius, and finally to the 72. We watch the core temperature closely and stop the heat exactly when the center of the fish hit 60 at exactly a bond. We kill the dangerous bacteria and make the meat firm enough to curl without turning the tuna into the mush.
In the canned tuna process, sterilization is the most critical step. The goal is to destroy harmful microorganisms, especially Clostridium botulinum or Morganella morgani, by ensuring the product reach the required sterilization value of F0. So the main challenge comes from the heat transfer. Tuna meat is densely packed and it behaves like a solid, so there's no internal convection. So heat transfer occurs in two stages. First is the conduction from the heating medium to the can surface, and then the conduction from the can wall to the center or the cold spot. The conduction step is slow and becomes the limiting factor in the entire sterilization process. Well, based on the heat transfer principle, we can compare the different retort systems. The first one is the saturated steam retort, which is the most traditional technology to be applied. It can be designed in both vertical or horizontal configuration, and the horizontal ones are more commonly used in the modern tuna processing. Well, the horizontal retort are standardized with the diameter from 1300 to 2000 millimeters, and the chamber length can be adjusted to 7 baskets. So as each basket weighs approximately about 450 kilograms. For the vertical one, the diameter is typically around 1200 to 1300 millimeters with a height of about 2.4 to 2.7 meters, and it can hold up to 2000 small cans per patch. So both systems include a steam inlet at the bottom, a steam distributor, vent valves, bleeders, and safety valves, along the temperature with the pressure sensors. During operation, the most critical step is the venting phase, where steam is used to completely remove air from the chamber. Any remaining air can create cold spot and lead to under-sterilization. However, a key limitation is that the temperature and the pressure is directly linked together, so overpressure cannot be controlled independently. The second system is the water spray retort, which is typically designed as a horizontal pass retort. While standard diameters range from 1300 to 2000 millimeters, the 1300 millimeter models is the most common, as each basket weighs around 450 kilograms, which is still manageable for manual handling. Larger diameters require automated loading system, so the system uses a circulation pump and multiple spray nozzles positioned around the chamber. Water is sprayed at high velocity, creating strong turbulence that mixes the steam air and the air uniformly. This allows the independent pressure control to the compressed air, which helps protecting the package. However, the system depends heavily on stable flow and clean nozzle, as any blockage can cause uneven heating. The final system is the water cascade retort, which is also designed as a horizontal batch system with a similar standard as above, including the length of the chamber that can depending on capacity, typically holding up to 7 baskets. And its key components could include an external plate heat changer, a high-flow centrifugal pump, and a perforated water spreader plate above the baskets. During operation, a small amount of water is continuously circulated, heated in the heat exchanger, and then distributed from the top at a uniform cascading flow. This high flow rate improves heat transfer efficiency and ensures even heating throughout the system. In addition, the system allows independent control of pressure using compressed air, which is critical during cooling to prevent cans damaging. It also uses a separated cooling circuit, so the cooling water does not directly contact to the cans and reducing the contamination risk. After sterilization, the cans can move to the washing and drying stages. First, they are washed with hot water to remove any residue from the retort process. Then, drying is performed using air knives. They are high-velocity air systems that flow a thin, uniform sheet of air across the can surface. This quickly removes the water without physical contact, so they can preventing the contamination and preparing the cans for labeling and packaging.
Okay, so thank you, Gia Phong. So, if we stop here, the project could still fail commercially due to a high operating cost. So, now I will walk you through the final state of our flowchart, downstream process, and quality assurance. So, the first problem is after the can exits the retort, the wet, the surface temperature are too high, mechanical contact bringing will smooth the ink and could read the same. Furthermore, how we are guarantee a 100% vacuum seal and 3-tone patch without opening a single leak like this one. So there are two solutions to solve this problem. The first one is at the coating stage. At the coating stage, we use non-contact and check technology like this one. Another one is in the inspection stage. We don't do it manually. A caustic and article sensor scan every lid. A perfect process can must have an internal vacuum causing the lid to slightly concave like these pictures. So now let's talk about the energy loop, recover and reuse. So if we run the system linearly and properly, heating then discarding it, energy cost will cut our entire profit margin. So how will we capture the energy loop? First, talk about heat recovery. In our water case say autoclave, this one, steam transfer to heat exchange, condense into clean water. Instead of running it, we recover 100% of the steam condensate and put them back to the boiler. Since it's already hot, the boiler requires significantly less fuel than 50% to reach the steam temperature. Even better, the cooling while coming out of the pit is warm and sterilized, so we pipe it to the tongue bin at the very start of the process. It provides free heat to break the capillaries of this tuna, the frozen tuna. So I have a small tip for you guys to increase the insulation and thermal efficiency. So let's talk about insulation. A retort operating at 121 degrees Celsius is a massive radiator. By simplifying, insulate the retort cell with the 3.8 centimeter layer, we immediately cut the steam consumption by 90%. So the reason why we heat our pudding liquid to 93 degrees Celsius is not just air remove. By raising the product initial temperature to 75% before it reaches the retort, we reduce the peak steam demand by 30% and the total package energy consumption by 29%.